In the second lecture on thin film techniques, we learn about sputter deposition. We learn about glow discharge technique of sputter deposition a little bit detail. When a surface is bombarded with high velocity positive ions, it is possible to cause ejection of the surface atoms. What you see here is the instrumentation of a sputter deposition unit. We have a vacuum chamber which is connected to a vacuum pump and an inert gas inlet valve. Most of the time, we'll be using argon as the inert gas. Inside the vacuum chamber, we have a sputtering target and a substrate onto which the thin film has to be coated. We'll be applying a very high voltage across the anode and the cathode. This process of ejecting atoms from the surface by the bombardment of positive ions, usually the inert gas ions, by momentum transfer process between the sputter gas and target atoms, is commonly known as sputtering. This process is also known as cathode sputtering. And argon is the most commonly used sputtering gas. Sputtering is commonly used for the deposition of devices fabricated from metals, alloys, oxidic and other compounds of refractory nature. It is now possible to make various resistive, semiconducting, superconducting and magnetic films by this technique. The mechanism of the process involves a momentum transfer between the impinging energetic ions or neutrals and the cathode surface atoms, as a result of which a physical removal of atoms take place. When the surface of target material is bombarded with energetic ions, several types of interactions of the ion with the surface can take place. What you see here is the target material comprising its atoms, which are shown in yellow color, and sputter ions, which are shown in blue color. When the surface of the target material is bombarded with these energetic ions, the incident ions are reflected. Probably it is neutralized in the process. The impact of the ion causes a target material to eject a secondary electron. The ion is trapped or buried in the target material. This process is well known as ion implantation. The impact due to the ion causes some structural rearrangements in the target material. The ion impact sets up a series of collisions between the atoms of the target. The released sputter atoms then get deposited onto the substrate. Sputtering yield. This is defined as the average number of atoms ejected from the target per incident ion, which increases with the increasing energy of ions and their mass. Sputtering yield also depends on the atomic weight of the target material. This figure shows the variation of the sputtering yield as a function of the incident ion energy. On the x-axis, we have the ion energy, which is expressed in electron volts, and on the y-axis, we have the sputter yield, which is expressed as atoms per ion. There is a minimum energy needed for each element to start sublimation, and this energy is called the sputtering threshold. This threshold is different for different target materials. Most of the materials have a sputtering threshold in between 5 and 25 electron volt. the lower limit being set by the energy needed for sublimation. The plot for sputter yield can be divided into three parts. In the first part, the yield increases quadratically with energy. In this case, the energy of the incident ion is less than 100 eV. In the second part, the yield is directly proportional to energy. In this case, the ion energy is greater than 100 eV. Finally, it reaches a saturation when the ion energy is between 10 to 100 kV. This is because with the increasing energy, the ions get implanted onto the target material, and the atoms which are ejected from the deep layers will not reach the surface. Besides this, the yield is also dependent on the angle between the normal to the target surface and the bombarding beam direction. This figure compares the sputtering yield of copper and molybdenum as a function of bombarding energy of nitrogen ions at two angles, that is at 90 degree and 45 degree. It is seen from this figure that the sputter yield is higher at 45 degree when compared to that at 90 degree. We'll now learn about the glow discharge sputtering technique, which is considered to be the simplest method of sputtering. This can be understood from the behavior of gases at reduced pressures under a high DC voltage source. Conduction through a gas is not generally possible unless a high DC voltage is applied between the two electrodes with a gas or air in between them. This figure shows the schematic of the glow discharge sputtering unit. It comprises of a glass tube which is filled with a gas, and it has two electrodes, a cathode and an anode. A current, which is known as ionization current, can pass through the gas or air only when a breakdown of gas or air molecules occurs, resulting in their ionization. And the minimum voltage at which this breakdown takes place is called the breakdown voltage. Before learning about the glow discharge sputtering in detail, let us consider the voltage current or ionization characteristics of a gas-filled chamber. The voltage current or ionization characteristics between two electrodes at a reduced gas pressure under DC power shows several regions as indicated by numerals 1 to 10 in this figure. Of these, regions 6 and 7 are relevant for sputtering, especially the last one for continuous deposition. Region 1 and 2. The current increase is negligibly small in this region with the rise of voltage in the initial stage, that is 1 and 2, until a minimum voltage as indicated by the dotted line 10, known as breakdown voltage, is reached. It is then followed by a large increase in current at a constant voltage continuous with VB in the Townsend region. This is the region 3. The graph then shows a sharp fall of voltage with the increase of current as indicated by regions 4 and 5. It is then followed by a constant voltage region, that is region 6, known as the normal cathode glow discharge region. Now, a glow appears on the cathode but covering it only partially. The next region, that is region 7, where there is a large increase in voltage as well as current, is called the abnormal glow region. In this case, the cathode is fully covered by the glow. A continuous sputtering can take place only in this region. The luminous glows in region 6 and 7 are self-supporting due to the ejection of secondary electrons from the cathode by the impact of positive ions. Subsequent regions 8 and 9 are of little importance for sputtering. The luminous normal and abnormal glow discharges show some broad visual features, namely bright and dark regions, the details of which may vary with factors such as gas pressure, cathode shape, etc. These consist of cathode glow, cathode or Crookes dark space, negative glow, Faraday dark space, positive column, anode glow, etc. as one goes from the cathode to the anode. The negative glow is the most intense inside the tube, the positive column being the second one. We see here the voltage fall across this gaseous column between the two electrodes, and we see that it is not uniform. The maximum voltage fall occurs at the cathode dark region. We'll now try to understand the various steps involved in the glow discharge sputtering. An electron emitted from the cathode under a DC high voltage while passing through the cathode dark space acquires high energy because of a high voltage fall and moves to the edge of the negative glow region. Then, ionization occurs by collision and only excited atoms or molecules emit light but not moving electrons. The above high energy electrons then make collisions with gas molecules and ionize them, releasing an electron from each collision till it loses its energy to a state which is inadequate for further ionization. Thus, in this region, a considerable number of positive ion-electron pairs are generated. These ionized or excited molecules emit light, giving rise to the negative glow. The positive ions resulting from such collisions tend to slow down the electrons. The electrons, in turn, lose their power to ionize the gaseous molecules and accumulate, forming a negative space charge region beyond the negative glow region known as the Faraday dark space. Electrons being light, however, move towards the anode under the positive field, acquire sufficient energy and begin to ionize gaseous molecules in the region corresponding to positive column. It may be mentioned here that since the moving electrons by themselves do not emit light, the region they pass through before colliding with the molecules will be dark. Positively charged ions formed in the negative glow region move through it to the cathode dark space by diffusion and are then accelerated to the cathode and strike its surface with a voltage nearly equal to the full voltage drop. This results in the sputtering of the cathode material as well as the emission of secondary electrons which maintain the glow discharge. Because of the heavy mass of the ions and their high momenta, their impact will cause a displacement of atoms in the cathode and a consequent damage of the target as mentioned earlier. The composition of the sputtered film generally conforms to that of the cathode material, and the deposition is primarily due to momentum transfer between the impinging ions and the cathode material as mentioned before. Since the process does not depend on temperature and as there is practically no mass transfer, the sputtered material will be of the same composition as that of the target. We'll now discuss about the factors that affect a glow discharge sputtering. The first one is pressure. When pressure increases, the discharge current increases, the voltage falls, and the cathode dark space decreases. The number of ions increases and is proportional to P square, but their energy gets reduced. The sputtering yield increases proportionally with the number of ions, but decreases with decreasing ion energy linearly or less than linearly in the actual experimental cases for a range of a few kilovolts. There is an increase in the number of total atoms ejected. There is, however, inherent limitations associated with the increase in pressure, so there is an upper limit for P. Due to the increase of pressure, the ejected atoms suffer more collisions and are thus prevented from reaching the anode. At a pressure of 0.1 torr, less than 10% of the ejected atoms reach the anode. The optimum pressure range for glow discharge sputtering is therefore in the range between 25 and 75 millitorr. The second factor is the distribution of sputtered atoms. At high pressures, due to the collisions with the surrounding gas atoms, the sputtered atoms are diffusely scattered during transit and therefore reach the anode with randomized directions and energies. At constant pressure and constant applied voltage, the deposition rate is low at large distance from the cathode. As the distance is decreased, a more uniform deposit first results, which then becomes annular in nature with a maximum thickness on a circle slightly smaller than the target. The optimum condition of deposition is about half the area of the target and cathode-anode distance is about twice the length of the cathode dark space. The glow discharge extinguishes and no sputtering occurs as the anode or any other obstruction approaches the cathode dark space. The third factor is the current and voltage across the tube. The rate of sputtering is proportional to the current for a constant voltage. The voltage dependence is non-linear, but for a range of applied voltages, depending on the target material and gas, glow discharge sputtering may be operated in a linear range. The sputtering range is proportional to the product of current and voltage. Typical magnitudes of the current density and voltage are respectively 1 to 10 milliampere per centimeter square and 1 to 5 kilovolts. Selection of the cathode is another factor that affects a glow discharge sputtering. The cathode material is usually a plate, foil or electroplated material. The area of the cathode is taken about twice that required for a uniform deposit. Due to the bombardment of ions, the cathode gets hot. The temperature increases rapidly to reach an equilibrium value. The rate of temperature rise and maximum temperature attained depends on the power dissipated at the cathode, thermal characteristics of the cathode, gas pressure, etc. There is no direct dependence of the cathode temperature and sputtering yield, but undesirable effects can result due to substrate heating. So, generally the cathode is cooled with running water and some other cooling fluid. Contamination issues. Though the sputter coating is carried out at a high vacuum, the outgassing as a result of plasma discharge heating of the container walls may contaminate the components of the sputtering chamber. The deposition of the oil vapor present in the gas also contaminates the film. The decomposition of oil vapors as a result of backstreaming from the diffusion pump operated at high pressures is another source of contamination. To avoid this, an optically dense baffle is used for the chamber. Deposit control. If current density and voltage are fixed, the rate of deposition is seen to remain constant with time. This can be achieved with the help of an automatic pressure controller and regulated power supply. Another technique to control the deposit rate is by controlling the discharge current density electronically. A quartz crystal oscillator may be used for the monitoring and controlling of the rate by means of a feedback mechanism to control the discharge current.